United States, and also we have in China, in India, Korea, Japan, Europe as well. So if you look at the different business units, we have chemicals, performance chemicals, metals, fertilizer, polymers, and specialties. So specialties is a newly actually established BU starting from 2016. So we're looking at all the very specialty engineering thermoplastics being supplied from this business unit. Part of our legacy engineering thermoplastic actually is now moved to polymers BU. And if you look at the kind of products we provide, being the innovative plastic side, we have our legacy Lexan resin. It's a polycarbonate being invented in 1953. And there's no real resin. It's a high temperature PPE resin, and there's Alten. It's a extremely high temperature thermoplastic. It's polyether imide. So I'm not really here to give you guys a chemistry class here, but really discuss how we can service this industry. So since a lot of people in technology actually are wearing glasses, maybe have you ever wondered what they're made out of, right? Actually, in many cases, the glasses are made out of polycarbonate. It's a totally transparent, almost glass-like plastic, and it will not break if you drop your glasses on the ground. And that is our Lexan resin. It is amorphous resin, meaning that there's no crystalline in there. That's why it's totally transparent. The transparency can get as high as above 90% transmission of light. So that's why it's being used in many cases for transparent or even colorful kind of applications. That's just an example. So I'll start with the fundamentals to introduce the material selection for today's electronics. The reason being that we have to look at what's being useful, because even for many emerging applications or technologies in electronics, people start out from taking off-the-shelf available solutions to make whatever they need to make, okay? So I don't really need to describe it. Everybody knows today's world is no longer what we had like previously. This world is connected by data, connected by wireless, wired, cable, everything. People being, having global conferences. The world has become flat, right? So no matter if you're right now, even if you're on a plane, you can get Wi-Fi if you purchase that, right? So it's a highly connected world. That's what we call the Internet of Things. It's rather Internet of everything. And if you look at the the highest volume consumer electronics devices, TV, monitor, desktop, laptop, if you look at the range of the consumer level devices you're using every day, from our perspective, the material requirements can be different according to the different level of power. For example, for a TV kind of housing material, you will have to have flame retardant properties on the thermoplastics. Otherwise, people have been complaining cell phones being burned or power surge, something happened to it. But in reality, in many majority of the industrial regulation does not require flame retardancy on a cell phone device. That doesn't rule out the accidental kind of incident where it still can get burned sometimes. But overall, in general, the power level is not high enough for that device to burn itself. So that's just to give you a very simple concept of how differently the material requirements can be different from one device to another. And if you look at the existing products like laptop or tablet or desktop, game device or cell phone, so what we typically do is, if you look at these kind of devices, although they are having different requirements, their ecosystem or their components are essentially translatable to a certain extent. Meaning that you will have a screen on your laptop, you will also have a screen on your tablet, and you're looking at a screen on your cell phone. It's just very simple, analogy here. But of course, even if you tear down a robot, I'm not sure how many of you were at the keynote speak from IBM. Actually, they announced their collaboration with SoftBank this time at CES. And this is actually the robot Pepper from SoftBank. If you tear down a robot, you will get similar type of components. Of course, it will have its specialized tools that's very specific to a robot. So we would say the electronic devices, they have their common components and ecosystems, but they also have difference among each other. Being a material supplier, we have to consider from very fundamental aspects to make functional materials that can realize the applications in each aspect. For example, display, structural components, antenna and sensor, wire and a cable, main board, either PCB or flexible printed circuits, or power. They're all totally different. And then among these different aspects, for each one of them, we dig deeper into the needs on the material side and come up with a set of specific requirements. That's what we call CTQ, critical to quality. And then we work closely with our customer to co-develop the solution to fulfill their needs. So what are the critical properties that would be necessary for a particular application? So for just to give you a very simple idea of what is thermoplastics. So from a plastic perspective, there are two big groups of plastics. One is thermoset, the other one is thermoplastics. Thermoset can change their chemical structure in the sense that you basically, they can be liquid, and then when you cross-link them and cure them, they become permanent. That's just a very, a common type of epoxy kind of thermoset. Whereas thermoplastic, you melt them down, so they have a TG, that's glass transition temperature. You melt them down, you form them into certain structure, for example, like a laptop cover, and then you can still melt them down to recycle them. And by the way, that's what we do a lot with automotive. That's where you get a lot of actually interior side of automotive are plastics. And we get a lot of recycle from there as well. For electronics, it's a similar thing. The ease of using thermoplastics make it one of the major material actually being used in today's electronics devices. And if you look at what kind of critical properties are really important here, mechanical performance is of course really important. And by the way, this chart I list here actually goes across different industries, not just for electronics. It shows how important it is, for each industry and the type of applications. Mechanical performance is almost always very important. Melt point, which would indicate the thermal kind of the heat resistance, thermal level, and then the fire retardancy would tell you if the fire will actually will go away within certain time. So we have regulation on each one of them. Chemical resistance, maybe you don't think everyday cosmetic is actually aggressive, but I can tell you they are actually very aggressive. So because thermoplastics is also organic material, it's polymer. It's essentially similar, it has similar kind of composition even to your skin. So if you look at the aging process, if you keep on abrasing your cell phone like plastic cover, it will, long enough, if it's not chemically resistant enough, it will crack, okay? So the other part is cost. Everybody think plastics is cheap. I can tell you it's not true. Some of the commodity grades are relatively inexpensive, but the functional specialty materials which we actually target to provide the smart, what we call smart material, can be quite expensive, depending on the kind of properties. And if you look at this triangle, this gives you a very, what we call is actually a thermoplastic pyramid. I will explain in more details. It will give you some idea, basically very simple. The higher the heat resistance is, the more expensive usually the plastic becomes. So if you look at polypropylene, polyethylene, or PET, they're relatively cheap. So PET, a very good example would be a water bottle. So a water bottle is usually made out of either PET or polypropylene. So after I finish this presentation, I can give you guys a bonus session. You can ask me what is made of. I will try to answer all your questions, okay? So now, if you look at, because polycarbonate has this BPA kind of issue, people try to use different plastic to make water bottles. If you see some say that it's like a BPA free and then it's a little bit blurry, that's probably polypropylene, okay? So other properties are also very essential. Otherwise, we would be, having no issues, just make one thing and works for everything. That never is the case. So dimensional stability, for example, when you think about it, things always move according to the heat. So if you heat up a metal, it'll expand, right? That's normal kind of metal. It's the same thing with plastics. So you want this to have the same kind of what we call dimension stability, meaning that the less it moves, the better the property. And then there's moisture uptake as well. I will discuss about why moisture uptake is so important maybe later, which is also related to its long-term aging properties. It could be under thermal attack, or it could be under moisture or chemical attack. And then there's also optical properties. As I mentioned, being amorphous polymers, you're looking at polycarbonate being very transparent. But there is also another group that's crystalline polymers, where you would see actually the polymers being opaque instead of transparent. And then there's electrical/dielectric properties and also scratch resistance, etc. Depending on exact end application, the requirements can be very different. Ultimately, we have to pass what we call trials at the customers to come up with the actual solution that can solve the problem. Okay? So I will not go through the whole set of properties, but I will pick, I think, the two most important things to discuss here. One would be just the mechanical properties. So the chart you're looking at here basically listed out all material range all the way from phones to elastomer kind of format, and natural materials, meaning natural material can be natural rubber or even wood or stuff like that. And then polymers, and then it goes to actually ceramics. So polymer is still actually organic. Ceramics becomes inorganic, and you can also look at composites. Composites can be composed of different type of materials. And then what they call technical ceramics is actually kind of extremely hard kind of ceramics, and then there's metals. So this is a rough range of the Young's modulus, basically how stiff it is, and the other one is strength, and how much strength till it breaks, right? When you think about the stiffness, describes if this material can withstand a certain force and break at a very short dimension, meaning that if you are looking at a piece of rubber, you bend it bends with you. So it's not stiff at all. But eggshell is actually pretty stiff, because when you break it, although the force is very small, it breaks instantly, and that distance is very short. So the stiffness and the strength are two major characters that would describe a material. And if you look at, because it's a little bit hard to see, within the yellow range is where we would describe polymers and composites. In that particular region is where we would be engineering thermoplastics. And this is almost the sweet spot where actually we can find applications for majority of the electronic devices. The other property I think it's quite important is to look at how material responds at different spectral range. The reason we do that is because if you look at the entire spectrum, we're looking at from electrical range. Basically, this is describing electricity. I put the application on the top, and this is the kind of response, what kind of response you can expect, at the dimension, both kind of dimension and also, as well as the type of material at the bottom. And in the middle, actually, if you look at, is the mechanism of how material will respond to the stimulation. And for wireless communication in particular, it's at the range for microwave. And if you look at the permittivity, it basically changes in this range for being polar molecules. And if you go to actually infrared, which is actually surpassing the microwave and getting into the optical region, it's more like an electrical response. So the organic materials actually would be relatively stable within this area, although there's still certain difference between them. It can be very subtle. It wouldn't matter like before. However, if you are talking about this particular range and the sensitivity and the kind of data communication, getting into the 5G kind of range, this could become very important. We can come back and see the reason behind. Mm-hmm. The OLED is kind of different. Actually, I didn't include the OLED. I included the quantum dot here. So you can, the OLED is actually also within this range. The response, the mechanism is the same, but the material is organic. Yes. So I didn't include all the cases. This is like a high-level description. Because I try to include as broad material as possible, although not everything can be included. This is just to give you an idea of how different materials would respond, especially at microwave range. So you're looking at the thermoplastic, including rubber, would have relatively low permittivity, and also, depending on what material you're talking about, would have quite low dissipation factor if they're dry enough. That's why I put water here, is because water is, if you look at the way that it vibrates, it's right in this regime. And there's also different kind of electroactive ceramics that actually has a very broad range of dielectric constant. They're very specific kind of ceramics. And even within the engineering thermoplastics, this is the data that we have internally. So we have actually at both 1 megahertz as well as microwave range. So if you look at the 1 megahertz, this is the type of materials that you would like to have actually because their permissivity as well as dissipation are both really low. And the nylons, because they're relatively, they have relatively higher water content, they're actually not preferred for certain type of applications at antenna design. And this, again, this chart is showing between 1 to 20 gigahertz. In that range, actually, majority of the thermoplastics are relatively stable, and the permittivity is gradually decreasing, actually, when you get to higher gigahertz range. Among these, we have Norio, which is high heat PPE, and Alten, which is a high temperature polyether imide material. You can see the dissipation factor is below 0.01. Actually, if you look at other materials, they either have a higher dissipation factor or they have higher dielectric constant. This is basically determined by the molecular structure of the high temperature materials. So from a solution perspective, we actually have been in this business for a very, very long time. It's just the OEMs, they don't like us to disclose their names. But in reality, we work with almost all the consumer electronics companies in the world. And we provide different type of like what we call electronics solutions based upon the type of application. And sometimes when you see there could be some overlap from one application to another, because fundamentally you still want one material to have as many applications as possible. Whereas, of course, there has to be some fine-tune from one specific application to another. And among all these solutions, for example, aesthetic solutions deals with a lot on the colorability side. So one thing is, as I mentioned, polymers are actually organic. They tend to be degraded. They can be destroyed depending on how you treat them. And the concept of plastic being as stable as inorganic material is unrealistic, but that's something that we try to keep it, make it happen at least within the lifespan of the product itself. So if you look at, so here we have aesthetic solutions, we have ultra-thin solutions, basically providing the structural support and structural components. And we have flame retardant. We have also eco-compliant flame retardant solution, because many FR agents have, the brominated kind of materials are very toxic to the environment. We have discontinued using all those kind of solutions. We try to come up with environmental friendly type of FR agents. We also have what we call robust blends solution. This is basically, on top of the chemistry of the polymer itself, we have a blending solution depending on the kind of end application we want and the properties we want. And there's also sustainability solution. This one would be, as I mentioned, we try to use biomaterials, or we try to use post-consumer recycled materials. And right now, we wanted to really focus on the functional solutions, meaning that to differentiate it, to differentiate ourselves from our competitors, we have to really provide value-added functions to the end applications. So how do we do it? I wanted to give you a glimpse of how we really do it. First of all, for neat resin to be made, it actually has many steps. For polymer is basically what we call macromolecules. It's usually very big molecules composed of what we call monomers. So it's almost like when you play with Lego, right? You put a red there, you put all red, then it's called homopolymer. You put one piece of red, you put one piece of blue, another piece of yellow. If you have three components, it's a tricopolymer. If you only have two kind of monomer, you have a either block copolymer or random copolymer, depending on how those chips alternate each other. So we have to make neat resin, but we normally don't really sell the neat resin. We try to come up with differentiated solutions based upon the resin we have. There goes the formulation side. So the formulation here is not necessarily limited to the compounding process. We can also, try, different technique to combine the resin, filler, additive, and interfaces, to play with the interfaces to achieve our goals. And you can see here, there's an extruder here. After this formulation is done, we blend them together, and we can extrude and make pellets, or we can make film and sheets. And the end product will be a uniformly distributed type of form. And then we also have internal application design capability, which means that this whole thing is not just the material, because the material will perform very differently depending on how your part is designed. For example, if we wanted to sell one material to laptop cover as well as a Bose structure internally, then both of these two designs, one material may perform quite differently. So we need to have CAE engineering capabilities to come along with the material itself to really be able to fulfill the needs of the end products. So again, the materials that we supply right now, there's polycarbonate Lexan resins. There's cycloid is basically polycarbonate and ABS blend. We also have high heat Noreol resins, crystalline performance resins, high performance polymers. This will be high temperature polymers. The temperature which can withstand the heat above 220 degrees Celsius, or even go all the way up to 350 degrees Celsius, which can be used actually in many electronic devices as well as aerospace industry. We also have compound solution, where we combine the resin and filler together in compounds, and it's used for injection molding process. And then we also have specialty film and sheet business, which can provide functional films and a sheet, which is like a thicker type of structure. So here comes the thermoplastic pyramid. So if you look at the performance level, for the electronic materials, because we serve a lot other industries, especially automotive, agriculture, aerospace, even consumer level, we don't, electronics, of course, is one of our biggest markets. Then the high temperature resins, along with our, mid-level thermoplastics, are right at the cost as well as performance range for this industry. And as I mentioned, for polycarbonate, people are only aware of BPA, where in reality, we do have copolymers. And if you look at, this is the Lego pieces I was mentioning. So the copolymers basically incorporate the functionalities to the backbone. You don't have problems with not being able to disperse it well enough. For example, the EXL copolymer will give you extremely good impact resistance. So one of the old phone back covers, which you've been used in white color, actually made out of our EXL copolymer. So if you drop it on the ground, it will not really break. So that's just one example of the kind of specialty business we're working on. Okay. This chart shows how we try to come up with, combined kind of solutions, what we call functional materials, by combination of the resins that we have, as well as, by the way, we don't only use our own resins. There are other resins available externally. We also would select, depending on how useful they are. And there's also all kinds of different inorganic materials, all the way from very common chopped or milled glass fiber. And if you move upwards, you're looking at carbon fiber, aramid fibers. You're also looking at, if you go to the top of the pyramid, you're looking at all kinds of different silver nanoparticles, graphene, carbon nanotube, all kinds of stuff that has been used. I'm not sure how much you guys know about those materials, but really those are very important, especially for the future electronics. So by different ways of combining the substrate material and the functional material, we can make what we call smart function materials that can exhibit different kind of functionalities. If you look at on the top, what I listed here, these are all already commercially available solutions we have. Of course, we may only have those in the injection moldable kind of solutions. We have dimensional control stiff kind of solutions, lubricated solution, anti-static, EMI shielding capable. We also have electrical conductive solutions. People tend to think plastics are all insulated, which is not really true. We also have thermoconductive kind of solutions available. And this is just to show I think I may have rearranged my slides a little bit. This page actually is showing how we wanted to look at from our base material to certain compounds. This is one of the structural solutions, what we will call the thin wall stiff solution. If you compare to the metals here, so the metals going all the way from die-cast level aluminum to steel, magnesium, and aircraft level of aerospace level of aluminum. The way I put it here, if you look at it's a specific modulus and specific strength, meaning that you divide their structural performance by the density, which is quite important in many applications because in today's applications, people are looking at miniature designs, and you really need solutions for a lightweight type of application. That's what we see actually in many requirements. This is a typical data sheet. You're looking at mechanical impact, thermal, physical, flame retardancy. Usually we would list it out, and we would also list with processing conditions, where you can, how you would make it actually as close as possible to the end structure that you design. Let me see. Okay. think, yeah, but anyway. So one of the example I want to give here is one application on the wireless technology side, because the theme of this conference is about Internet of Things. When we think about it, the closest we have for right now for that particular direction is really the material for antenna applications. And we do see this trend. By the way, this is still right now, is 4G. But after that, I think people are looking at 5G, the potential possibility of 5G being possible within the next maybe 5 to 8 years. So we do have solution actually. This actually should connect to the dielectric property page. I apologize for that. So this one is showing the kind of compounds we have, because one of the base material resin we have, PPO, has really, really low dissipation factor and dielectric constant. This is within the 1 to 3 gigahertz, basically Wi-Fi and Bluetooth range, how these would react. And if, this, by the way, there are other properties. So sometimes we've had requirements or requests from our customer to have either high or low dielectric constant, but it's almost always they want to have a solution at low loss range. And we can understand because they don't want dissipation to happen. The other example I wanted to talk about is actually a Sabic LDS antenna solution. So when you design an antenna, basically you're using a substrate material and you want to have conductive paths, which is in many cases copper paths on top of it. Now how do you do that? Traditionally, you can basically go through a very cumbersome process to design the circuit and then to plate the copper on the surface. This one, what we would call a laser-directed sintering process, this would describe it in a better way, is that you can select the material from our portfolio. You go through an injection molding process. This is like a prototype for a cell phone cover. And then, excuse me, you use the laser to etch whatever structure you wanted to design as your antenna conductive path for the antenna. And you do metallization on this entire part. This metallization is more mild. It will not be able to actually metallize the entire part. It will only metallize the surface that's being activated by the laser. So in the end, you have a capability of design a 2D to 3D kind of antenna structure according to whatever you wanted to achieve. This is basically our current portfolio. We have based on the solution based out of polycarbonate, based out of polyimide, which is a nylon material. We also have a PPE type of solution to give you that kind of different properties, basically. So I tried to give you an overview of how we provide electronic material solution to today's electronic market. So basically, when we look at the teardown type of solutions, we can provide solutions to almost all components of electronic devices, except for very, very inorganic part. That's really not our play. But what happens if an electronic device really becomes like this, and which is totally possible, and it's happening right now. Even in the industry, there are already companies focusing on this type of, what we call wearable devices, where the device just disappear, right? So the piece of film you're looking at, it may be not only for display, but also for power or even antenna. Everything is there. How do you achieve that? So I guess if that's really true, then we are going to get out of business with our existing solution. That's why we have to also look ahead, and we have to even think way ahead, because it takes forever for us to come up with a new solution. For electronic, at the keynote from Steve, the guy who invented the camera, he was talking about 20 years from now. I think for us, our materials were invented back in 1950s, 1980s. And it takes for a very long time for a material to be commercialized. So depending on the solution, we can come up with different kind of, ways to make those materials. That's why we have different ways to make different solutions. However, for this kind of change, it will be completely disruptive. Then how are we going to continue to provide innovative solutions? So I would, for this part, because it's more new and because of the corporate compliance, I cannot really talk about in greater details how we are going to do that. I'm just going to give 2 cases to introduce. The case 1 is for data communication from electrical to optical. There are different beliefs in this. I think there's debate. I don't think everybody agrees that the optical will definitely come, let's say, next year. The reason I'm saying that, the optical fiber has been there for intercontinental data communication for a while, actually ever since maybe 1970s or 80s. But then if you look at, for today, the requirements for data communication, the speed, depending on the distance and also the transmission, the speed, there's a certain range. You don't really need optical way to transmit the data. People can rely on lower cost electrical solutions. However, from what we see between 2013 and 2018, by the way, this is from Cisco, it's not from us. I need to give them credit. So people in the industry, from what we see, believe that the data is going to explode, right? It is going to explode starting from maybe 2015 to 2020, both wirely and wirelessly. The reason we're saying that is because the revolution for electronic device, even till now, we're still looking at a similar type. Okay, if you look at a device in this shape, it has certain components, it has critical ecosystems, and even when they go thinner and thinner and thinner, it's still the same device. It's the requirements on material becomes higher, but this change would be completely different. And then, why do we say that we tend to agree that the optical might come, or maybe you guys can educate me, is because we believe the data, if it has to explode both wirelessly and wirelessly, and even at the PCB board, if it has to change, then we have to move from electrical to optical. So this is showing that we actually do have current solutions. As I mentioned, we make amorphous resins, which is transparent. The transparency means a lot of things. It can mean transparency at different spectral range. For this particular design, you're looking at a current design, which is a typical grain PCB board. Everybody's seen that. And this is a polymer waveguide. Now, the part that I do not know is when this would come, because people keep saying it'll come, but we still don't see it as of today. However, it has something to do with how you design it, because when you have today's PCB board, imagine you wanted to connect it to a optical fiber. You have to have a transceiver in between to translate the optical signal between the optical and electrical signals. Our current solution, the Out10 resin, comparing to glass, it's extremely easy to make because you can injection mold it into lenses. It's hard to see on this page, but this page would show you very clearly how it's made. There's a small lens in the middle. It's just easier to make the case as well. So basically, you have electrical signal going from this direction, and this is a receiving, and this is a transmitting end on both sides. So in today's PCB board, you have to have the translation like that. Tomorrow, when you have a piece like that, you're not going to have a glue device to put this lens on the PCB board. Then what we believe, that in this case, there are different process and mechanism to make it happen. This process, for now, what we see, what we call would be a SMT capable kind of processing. SMT meaning service model technology, and it's actually, I shouldn't use this piece because it's a different process. And we see this SMT process being used not only for circuit boards, but also for very tiny modules in the thinner devices as of today. Like cell phones, there are a lot of SMT being used in very tiny devices. It's easier to assembly, and it can be automatic process. So in the end, this little part right here is actually providing a lens that you can also make it from glass, but it's much more expensive, and you cannot design the shape and the structure. But if in order to be able to do SMT, then our current resin is still not high heat enough. We have to go from R10 to X10. And X10 is way more expensive. It's basically at the tip of this pyramid, along with other resins. By the way, other resins are not transparent. They're not amorphous. They're crystalline. So we are almost the only solution at this moment for this particular application. This one is showing the optical property at elevated temperature. Again, the wavelengths, the most important part is actually the IR range. Why? Because the IR range, if you're just use your tune, it will give you heat. It is where the dissipation happens the most. You need a very high transmission at this range to avoid basically the dissipation to heat for your signals. And our material has pretty good transmission, and if you compare to different grades, of course, the high temperature resins, even if they're transparent, they're always pretty yellow. It's nowhere near the polycarbonate grade that you use for your glasses, okay? But again, this is where we are trying to do, and this is the first case I wanted to show you. Now, there's another case I wanted to show you to show not only on at the material level, but also we're trying to come up with different forms to serve this industry. This is actually one of our newest solution. It's a transparent conductive film for large format and formable sensor and display. So it is a functional film, actually incorporated with electrical conductivities. And its electrical conductivity, the resistivity, is lower than the current ITO solution by almost 5-fold. That will provide a very quick response. And we can potentially use it for, and by the way, because it's a polymeric solution, it's basically a functional polycarbonate film, it's flexible. Imagine when you use your touch screen, it's almost always glass. Reason being that if you use if it's not flat, then the current conductive material, which is ITO, will break. It will cause bad pixels, and it will actually malfunction. So in our case, we try to provide solution at a material level, and in this case, we can potentially use potentially make a device with certain curvature that is still touch sense capable. And the material here that we use actually is a silver nanowire. It can self-assemble into a random structure. And because it's a silver nanowire, it can be flexible. It will not really break as compared to the ITO paste. The ITO paste is, this is at similar dimension. It's very stiff, actually. So I think that pretty much concludes my presentation for today. I apologize, I don't really have updated business cards available, so if you want to contact, I show my contact here. But thank you for your attention, and if you have any questions, please ask me, okay?
Any questions from the floor? Any comment? Anything you'd like to clarify?
Yeah, here's the bonus session. Just ask me a question, what is it made of? Don't give me too hard a question, please.
Maybe let me start by asking. You know, nowadays one of the in thing is 3D printing.
3D printing?
Yeah.
Yes.
How do you see that?
Yeah, 3D printing, first of all, I think in many cases, the consumer level, they're using ABS, so it's a relatively cheap material. You can also use polycarbonate for printing, but it's not so easy to make fibers. Now, 3D printing is actually by itself a big topic. Depending on if you're looking at it from an enterprise level or a consumer level, it can be very, very different. And, you know, what is exactly your question?
Is it feasible that in the near future, you know, we can actually just print our own, you know, cover or container or whatever panel for our own, you know, design without going through big company?
Well, as I said, it really depends on your purpose for the part, right? The reason I try to give a tutorial session is because I wanted to show you that how different the material can be, right? For example, some plastic are not even going to adhere to other plastics without a glue. So if you wanted to use 3D printing to fix your device, you will have to be able to understand, because, for example, if your device is just a piece of phone with a plastic cover, what plastic is it, right? But actually, in many cases, it can also be painted. In our case, our polycarbonate, you don't have to paint it, it's colorable. That's like one of the aesthetic solutions as I was showing. But then you will most likely have to use the same type of plastic, and you have to also make sure that plastic is 3D printable. Because 3D printing is almost like a mini extruder. The way it does it is it print out lines, and then you go round and round, right? So technically it's doable, but I think in many cases the stiffness and structural integrity of that particular part cannot compare to the originally made. Yeah. Unless you have a $50,000 3D printer, that may be possible.
Yeah, but there are publications that say that big company, they actually use 3D printing to print aeroplane parts and things like that, right?
I think that's, for aerospace, I'm not sure, but for automotive, it will be too slow.
Too slow.
Right now, if you look at the automation, that's what we call it, industrial automation, it's very fast. So we actually are looking at industrial robotics to be evolved to the next generation of Internet of Robotics to make the next generation automation. Because 3D printing process takes forever with current technique. But that is not to say, of course, I understand they're also developing new 3D printing methodologies, not just line by line, but there are all kinds of different. If you're, since you're from academic, there's I think in UNC, University of North Carolina, they have, it's a liquid process, you pull it out, just like that, then yeah, it may be possible.
You have a slide on this, I think the antenna on the plastic casing, right?
You mean the LDS?
Yeah.
Yes.
You know, a few years ago when iPhone just come out, they have some problem with the antenna on the cover, whereby if you hold it a certain way, it doesn't work.
Yeah, well.
What was that about?
What do you mean it doesn't work, huh?
I think the first model of that particular, I can't remember, iPhone 4 or something, whereby if you hold it in certain iPhone 3, yeah.
You mean, no, I know what you're talking about. You're talking about iPhone 4, if you put 3 fingers there, it will not work, right?
Yeah, something like that.
That is because it's made out of metal casing, right?
I see.
So you're basically blocking the signal outlet. If you look close enough on the phones with metal casing, there are slits on the side. That's actually where your signal can come out.
Right.
The first generation of iPhone 4 design, they have 3 on there, and that's exactly where you would use 3 of frequent. And then in the iPhone 4S, they add another one, so it becomes 4. Then that problem was solved.
I see.
Although they never say that, but we know how they fix it.
Okay.
There was this question. The problem was just 2, and when you hold it, you move both fingers connected. You're making actually a short circuit.
All right.
Which you you're like deactivating the intended function.
Right,
Yeah.
right.
So that's a short
Yeah.
circuit.
Yes, you're right.
You have to move one of the fingers either way.
Yeah.
Can I ask a question about
Sure.
medical certification? How rigorous is it?
It is very rigorous. Actually, we have, just like a flame retardants, it's a UL standards. For medical, we have, depending on, we have healthcare, we have food contact. So FDA has a whole set of particular requirements. And that goes all the way down to our manufacturing process. We have to make sure certain steps, that amount of, ingredients are not detectable at a certain level. So there are a set of very stringent actually testing we have to do. We have to get the approval process. But we don't see that very common for electronic devices, unless it's being used in a hospital. So there's a subtle difference, and we have to go to the customer to understand is exactly if they would require certain certification. Yeah. Does that answer your question?
Yeah, yeah.
Yeah. Hmm? Sure.
Any other question from the floor? No? If not, I think we will just finish here today. Yeah. Thank you very much, Dr. Sun.
Thank you.
I think it's a very interesting topics from our consumer electronics point of view. Yeah. But you were saying you had some bonus question regarding some plastic, right?
Yeah, you can ask. Actually, there are more plastic than you maybe imagine. So just point out to what
we
one
thought
thing
they are
asked
all
me,
the
I
same.
try to answer.
For the drinking bottle,
Uh-huh.
the one that you buy, sometimes it can be quite expensive. What is the difference between
That's what I'm
bottle
saying.
like this?
A thicker one definitely would be a more expensive than a thinner one. So if it's polyethylene, what we call polyolefin by blow molding, usually you get really squishy, soft bottles. And the more expensive ones are PET ones that hard. So you should feel it's thicker, and it's usually PET.
But does it have something to do with toxic? So
There's
they are
no-
claiming that the plastic, if you put water, they might be toxic.
Those are all food contact grades. And by the way, polypropylene has a very simple molecular structure. If you wanted to know which polymer you want to avoid, personally, I would avoid actually those kind of pillows, what they call memory foam.
Okay.
They're usually made out of polyurethane. There are very good polyurethanes, but the problem is, as consumer, it is hard for you to decide which ones are good, which ones are bad. So if you smell it really strong, try to stay away from those. If it doesn't smell as bad, or if you leave it outside one day and you no longer smell anything, usually it's okay.
Yeah. So why do some newspaper article claim that you shouldn't reuse water bottle? For example, like bottle like this, after you use it, after you drink it, you shouldn't fill it up and then reuse it again. Is there any scientific
What do you mean?
reason?
Because some newspapers, magazines,
Yeah.
Uh-huh.
claiming that if you drink water out of a plastic bottle, somehow the plastic's going into your body.
Oh, well, that comes to the aging side, right? When I was talking about it, it's still organic materials, right? It will not compare to, even metal will fatigue.
Right.
Even plane, we'll have to change it every maybe 20, 30 years, I don't know. So if you leave a water bottle in a hot day in your car with sunlight, it is aging process.
Right.
It's a thermal agent, it has a very strong moisture, right? And water can be very corrosive. It's actually more corrosive than you would imagine, given enough time. It might cause problems. So I would not recommend.
Oh, okay.
Yeah.
Right.
Once or twice, maybe, it's your own choice, but I would not. Okay.
What about microwaving plastic?
That's a great question. So actually, I showed, one of the page I showed, I have the water here. Where is it? So the microwave, if you look at, here it is. So the microwave range, depending on your microwave, okay, so majority of them would act in this range. So you can see that, of course, this is a very rough image. It will not give you all the answers. The thermoplastics, the plastics, do they respond to the microwave? No. They are relatively stable in this range. Now, what if you have water in there? It might be a different story. because water gets excited. That's how you cook your meal with the microwave. The idea is that only water would vibrate, but that's not true either. But then after many studies, I think eventually the conclusion is microwave should be safe unless you use it like in a crazy way, burn your food or something like that until other chemical reaction happens. Yeah.
So we should use certain type of plastic for
No, that's what I meant for plastic. Like actually for food containers, that goes back to Abdul's question is, we have to go through a very stringent process. So the grades that can be used for food or water are actually having an extra level of cleanliness. So unless you try to damage it with all kinds of severe, conditions, normal use is okay.
okay.
Yeah. But when it comes to the heat resistance, for the cheaper material, you don't want to get hot water or hot tea. Usually you have to use different type of cups. There's a good reason for that. Yeah. Okay?
Okay. I think we finish here, otherwise we will never finish. Okay, thank you very much.
Okay.